Now it's okay. So we start here. We will take few questions which were left out and quickly, and then yes. So we have finished in 24 question and 26th, rather 25th question we have finished. Now 26 to 29 they are of the same nature. We will try to taking few of them. 26th question, let me take it. It is like this. Question 26, yes. It is fx is equal to k cos x upon pi minus 2x if x is not equal to pi by 2, if x is not equal to pi by 2 and is equal to 3, this is how if x is equal to pi by 2. So you have to find the value of k so that the function is continuous at the indicated point. So in all the questions from 26 to 29, you have to, there will be some unknown like k is here and you have to determine. What is given is that the function is continuous at 3. It has been given in the book that function is continuous at 3. No, sorry, here function is continuous at the indicated point, and the indicated point is at x is equal to pi by 2. At x is equal to pi by 2. So we had to make sure function is continuous here at x is equal to pi by 2. So we had to see that what we can do best here. So find this. So first let us calculate the value at pi by 2. What is the function? It is pi, not pi by 3, it is pi by 2. So functional value at pi by 2 is what? Please see, it is 3 straight away. It has been given. So it is 3. Now let us calculate the left hand limit and right hand limit. So let us calculate the left hand limit, please. Limit x tending to pi by 2 plus. So what it will be from here? It is defined like this: k cos pi by 2 and pi minus 2x. Just a minute. I will write first of all pi x. This is your function. This is what you have to find it out. Now, first of all, please see. Here both numerator and denominator, what they are. Are they continuous function? First we had to make sure this thing. That yes. Cos x is a continuous function. We know it. And when a continuous function is multiplied with a constant, that is if fx is continuous function and k is some constant, and then k fx is also continuous. This is our theorem. So point is that the numerator, whatever the function here is written in the numerator, it is a continuous function. And likewise here, denominator is what? It is a polynomial, pi minus 2x. Please see. Here your variable is x. At times suppose it is written theta is tending to pi by 2 and theta is not occurring anywhere in the denominator, then it will be a constant function. Then don't take x to be a constant or something of that, x to be variable. Okay, see here x is a variable, so this is a polynomial. Pi minus 2x is a polynomial. So polynomial is also continuous function that we have defined. So and this rational function, this quotient of two functions, if numerator is continuous, denominator is continuous, and denominator is not equal to 0. See, all these things are automatically happening. Here see, x is not tending to pi by 2. That is 2x will not, when x is tending towards pi, x is tending towards pi by 2, then naturally 2x will tend where? Pi. So this will never be equal to 0 because 2x is not equal to pi. It is only approaching to 2 pi. So it will never be 0. So function is well defined and it both numerator and denominator are continuous and are continuous function. As such, this whole function by the quotient rule will be a continuous function. And as such, we will be justified in putting up the limits therein. So because in continuous function what happened? This limiting value is equal to the functional value, and that is why we are justified in putting this value herein. So it pi by 2 and pi this thing yes we have to, because see now if we put it pi by 2, then this thing will become 0. Here see this thing will become 0, pi minus 2 pi by 2, we will put pi minus pi, that will become 0. So we won't be able to take the limits. So see this will become undefined. So we have to be a bit careful for the simple reason that here see we know that sine theta by theta, when theta tends to 0, then this limit is 1. Sine theta by theta is 1. So we will try to modify our this function in this particular manner, and this can be easily done. How? Cos x can well be written to be what? Sine pi by 2 minus x. Okay, and close it. In the denominator you have pi minus 2x, keep it as such. Now see, and then what will happen? Limit x tends to pi by 2. Okay, now this limit you have to calculate. So what it is? This is now pi, this thing can well be written to be what? K sine pi minus 2x whole upon 2, and in the numerator what you have? Pi minus 2x. So upon 2 you can write, you can multiply by 2, and then see this much of thing we will show. K by 2 is a constant and limit x tends to pi by 2. Now see we know that this, then what you do? You put t is equal to pi minus 2x upon 2. So this thing will become what? Now k can be taken outside. See k into this whole function. K by 2 let us take outside. K by 2 let us take outside, and then this becomes how much? Let us see. In terms of t, when pi is this thing, so if we will write whole thing in terms of t now, sine t upon t. And t will tend 0, why? Because x is tending towards pi by 2. So this thing will t will obviously tend towards 0. Pi minus 2, pi by 2, and 2 will cancel, pi minus pi. So numerator is 0. So pi 0 upon 2 is 0. So this thing, and this is nothing but k by 2, because this limit is 1. This sine t by t tends to 0 is 1. So, and yes, so this thing should be equal to 3. Because left hand limit, and see here interestingly both left hand limit and right hand limit will be k by 2 only, for the simple reason function is defined in the same manner. Because whether it is left side or right side, x is not equal to pi by 2, function is defined in the same manner. So what you have to do? K by 2 should be equal to how much? 3. Limiting value, this is the right hand limit or left hand limit, whatever you want. This in fact you can calculate the limit itself. So this should be equal to the functional value. So k will be equal to 6, and that is the answer. So this is how you would be doing all these questions, right from 26 to this much. And so please, now we will take one more question, and then we will see that all remaining questions are of similar nature. So there is hardly anything to be tried over here. We will straight away come to now question 30. Again, please see, and then question number 30. Rest all of them are too simple. So there will be hardly any difficulty. Now, this type of question are often asked as far as your board examination, and they are too easy question. How your function is defined? Fx is equal to, yes, it is defined as 5. Constant function if x is less than or equal to 2, and it is equal to ax plus b if 2 is less than x is less than 10, and then it is 21 if x is greater than or equal to 10. So this is how your function is defined, and you have to determine the value of a and b such that the function is a continuous function. Now what is given? This function is a continuous function throughout. So what you have to find? You have to, there are two unknowns a and b here in the interval, open interval 2 to 10. So these constants, the value of these constants have to be determined. So now one obvious thing is, see when x is less than or equal to 2, the function is a constant function. So on the left side of this real line, this is mark 1, 1, 2. This side, the function is defined as constant function. Constant function, you know, it is a continuous function, so no issues. Ax plus b, it is a polynomial. It is a polynomial, so in this interval also 2 to 10. Suppose this is mark 1, this is 2, and this is say 10 mark. So in this interval also, the function is a polynomial defined, and if it is greater than this thing, then again a constant function, so it is a continuous function. So that way you can check it also. Now what we need to do, please see, we have to determine the values of a and b. So what we need to see, we see on the point 2, please see, on the extreme point 2, function on the right side is defined by ax plus b, on the left side it is defined in the other manner. So what we need to do is, let us calculate both the limits at 2. First let 2 plus. So 2 plus will be how much? If the function here is what? Ax plus b. Please see, 2 plus means on the right side of 2. And the right side of 2 function is defined as ax plus b. Okay, so 2 plus ax plus b. This is a polynomial. So what you can write? Function is continuous. So limit continuous means what? Its limit will be equal to, straight away you can write 2a plus b. Okay, and then limit x tending to, and what is the functional value? F at 2. F at 2 is defined what way? X is less than equal to 2. So it is 5. Function is 5. Okay, and then what? So here see, function is continuous throughout. So this limit should be equal to its functional value. So one equation which we will get is 2a plus b is equal to 5. This is first equation. And the second equation where we will obtain? On this extreme point 10. So limit x tending to 10 minus will be what? Again you will be, it is ax plus b. So it will be what? A polynomial. Polynomial is continuous, therefore it will be what? 10a plus b. And then limit x tending to 10 plus you can determine. And in 10 plus it is 21 straight away. So 21, so it is will be 21. So other equation you can obtain from here. At 10, the functional, since the function is continuous, therefore what will happen? Both left hand limit and right hand limit should be equal to the functional value, and both left hand limit should be equal to right hand limit. So either you put 10a plus b is equal to 21, or you put what else? You calculate the value of the function at 21. 21 function is calculated, it is at 10, sorry, at 10. Limit, yes, it is 10. So at 10, the function will be 21. So again, see, you will get the same thing. You will put either, you will calculate the left hand limit, see, functional value at 10 is also 21. So you are not going to get a new thing. Whatever you are going to obtain by putting left hand limit is equal to right hand limit, same thing you are going to obtain by putting left hand limit is equal to right hand functional value. So in a way, 10a plus b is equal to 21. This will be your equation 2. You can solve two unknowns, a and b, two unknowns. So you can solve them easily. You multiply this equation by 5. So you will get 10a plus 5b is equal to 25. So what? Subtract it, minus minus. So minus 4b is equal to minus 4. So b is equal to 1. Put the value of b here, 2a is equal to 4. So a is equal to 2. So this is your answer. So this is how you will do it. Now I will take one more question here, your last question, which of course employs the properties of modulus function. See, I'd like to tell you that modulus function, it is continuous throughout. It is continuous throughout. So mod x is continuous function. From the graph itself you can see it, because you know what is the graph of the continuous, this modulus function, and sooner you will learn that, see, this modulus function is not differentiable at 0. See, that is the only thing. It is continuous throughout. It is differentiable everywhere except at the point x is equal to 0. You will shortly learn here. So I am taking your 34th question here. now with 31 to 33 question, see, they are very simple. What you have to show, see, take any one of them. Okay, let me take the first 31st. Cos x square is a continuous function. You have to show that cos x square is continuous function. Okay, very too simple. Now see here, today see, I will be taking the derivative of this function of function or composite function. This is a composite function. You call it function of function. Here, what is the internal function? X square. What is the external function? Cos of x. Now see, students, x square is a polynomial, therefore it is continuous. I have told you, if internal function is continuous at x is equal to a, and moreover external function is continuous at GA. Suppose, see, what the theorem says, I am repeating it, limit f gx. Suppose this is, or gfx, you are more prone to take this thing. Suppose gfx, limit x tending to k, gfx you have to calculate. Here, if normally what you do, you put internal function is equal to t. Okay, so what the thing is, two limits you have to take. Limit x tending to a, g, fx. This internal function, this limit should exist. Now here, if it is continuous, because in the theorem, if internal function is continuous and as well as the external function is continuous, but continuous where? Internal function should be continuous at point A. So here it should be fa. If at all internal function f is continuous. And what about external function? See, internal function let me put equal to 2. So this is gt. And gt, here t should tend towards where? Please see, it should tend towards fa. So gt should be continuous at what point? Fa point. This is more important. So it is g and what? T tends to fa. So at place of t, what will we write? Ft. So this is what is to be taken care of. Now see, x square here. You have to show that cos x square is a continuous function. So here internal function is x square being polynomial is continuous throughout its throughout the real line or its complete domain, and the domain of x square obviously is the entire real line. Cos x is also this thing continuous throughout its domain, that is the real line, and as such it will be also now if suppose you have to determine limit x tending to say p naught, so x square will be p naught square, internal function p naught square, and external function will be what? At suppose x square I put t, so limit cos of t and t tends towards where? P naught square. So it will be should be cos p naught square. So it is directly putting the theorems which you have learned, nothing beyond it, and much more and all these things that why this, if internal function is continuous and external functions are continuous, at what point internal function being continuous at x equal to a and external function to be continuous at fa. So this result is derived from the general theorem on the limit, because that general theorem you visited, I will not take much time here, but I am just dropping the hint that this result is also not a original result. It has been derived from the limit of the result, from the result of the limits. Okay, so with this understanding, this function, both internal and external function being continuous, therefore this function of function will also be continuous. So this is exactly what you have to do in all the questions from 31 to 33. 34 question we will come back. We are coming here. Yes. So therein again see, I would like to enlighten you. Now see, you can once again ask me, because a good number of students have not attended the classes. I have already told you while taking up the limits and all these things have been kept in my lecture, that whenever you have a graph which is continuous, means this is continuous. Cos x, sin x, all these continuous graphs, like this thing, this is a continuous graph. Means in a layman language, you can understand like this, that if you can like in 10x. 10x is, if you look in 10x, then see its graph is like this. And if you go beyond this thing, then it is like this thing. So all these graphs, you cannot trace it without lifting your pen. So this is one way out to find it out whether the function is continuous. If you can draw the entire graph without lifting your pen on a plane, then of course it is a continuous. Or in other words, there is no abrupt change in the value of the function anywhere. Because discontinuous points are precisely those points where the functional value changes abruptly. So here see in 10x it is going plus infinity, this way it is going minus infinity, right say. So these are obviously discontinuous functions. So, and for proving this thing, now suppose cos x, this is the graph of cos x, everybody knows. Now if you want me to prove that y at this point function is what, so it is whatever this point a, so this point will be cos a, I will take epsilon interval here, I will draw lines here, let them intersect here, I will take like this, and say this point is delta 1, this distance is delta 2, and I will take delta to be less than delta 1 and delta 2 both. I have told you, so this much of interval if I choose in, then obviously what will happen? All the functional values, if you look in, this value will fall here, and the extreme value here is this one, this will fall here. So they are well contained within this, because this is cos a plus epsilon, this is cos a minus epsilon, this. So you basically find a deleted delta neighborhood of a this particular way. So this is how you can do in all particular manner. So this is not our point, we have already done all this very thing as far when we have taken up the limits. So but the point is, you should know, yes, why it is continuous. Why it is continuous? It is continuous because for every epsilon interval of a, we can find a deleted delta neighborhood of a, such that the limiting value which we are claiming takes place, that all the values, when x belongs to that deleted delta neighborhood, then functional value obviously falls within the epsilon neighborhood. So this is what precisely the rigorous way of proving that why all these trigonometric functions, why all these functions like modulus functions, why they are continuous. So that is the rigorous proof. Since that is not in your course, so you can make use directly, but for the better understanding of the issue, you need to do it. So now quickly revisiting the point, it is question number 34. Question 34. It is, find all the points of discontinuity of f defined by fx is equal to mod of x minus mod of x plus 1. Here see, it is basically nothing, very simple. Now what you need to do is, please see, you simply write your functions, getting rid of this modulus thing. Simple it is, now it is 0. When x is greater than 0, then what is this thing? This thing can be written to be mod x, can be written to be what? X minus. This whole thing will be positive. So, because x will be positive, x plus 1 will be positive. So, this is x plus 1, x is cancelled, and this will be minus 1. Where? When x is greater than 0. Or even at equal to 0. Now, please see. So, this side is covered. Now, you write minus 1. When x lies in this open interval between minus 1 and 0. And now x is lying where? In the open interval minus 1 to 0. Then let us see how our function can be defined. Here see, x will be what? Negative. See, in this interval what my x will be? X will be negative. So if I get rid of this modulus sign, so what I will write at place of x? I will write minus x, because suppose here it is x minus 0.5. So minus 0.5 will make it positive, and that is why this x modulus x here, because this is my function. So this function for the interval minus 1 to x to 0, here in this mod x I will replace with minus x. Minus. And this mod x plus 1, how I will be replacing? By x plus 1 only, because this will be positive. X plus 1 will be positive. X is negative, but it is plus 1. Negative, but of course its absolute value will be less than 1. So this thing will be positive because of plus 1. So you can write like this. So this whole thing minus x, it will become minus 2x minus 1. So for this interval, this is your equation 2, this is your equation 1. And similarly, if it is less than like this thing, If it is less than -1, then let us see how we can write it. When it is less than -1, then mod x can be replaced to be what? Minus x. And this thing x plus 1 will be what? This time this x plus 1 will also be negative. Because see, when it is like this thing here, so it will be negative. It will be negative. So what you need to do is that here since it is negative, so mod x plus 1, you will again put a minus sign. So that minus with this minus will make it plus, and you will write x plus 1. So this x and x will cancel, and what you will get is plus 1. You will get plus 1. This is equation 3. So this is, and this will be for the what interval when x is less than minus 1. X is less than minus 1. So here, this is how you would be defining your function. Once you have defined this thing, then rest of the things are quite simple. Now see here, for x greater than 0, function is constant function, that is minus 1. So obviously it will be continuous, because the constant function you have all. Just a phone call is coming. Let me attend it. मैडम मेरी क्लास चल रही है अभी, मैं आपसे थोड़ा देर में बात कर लूँगा. हेलो, मत आइए मैडम, मैं जरा क्लास ले रहा हूँ, अभी मत आइए फिर आप, इफ यू कांट डू इट. यस. Now see, when x is greater than 0, then your function is defined what manner? Minus 1. So minus 1 is a constant function, it is continuous. For this interval between minus 1 and 0, in this open interval, the function is defined at what manner? Minus 2x minus 1. This is a polynomial. Polynomial again you have shown to be a continuous function. So it is continuous in this open interval. Likewise, in the third interval, you have seen what it was. It was plus 1 when x is less than minus 1 on the left side of minus 1. So it is how much? Plus 1. Okay. So plus 1 again being constant function, it is a continuous function. Only the point of interest will be the points which are on the right side. The function is defined differently. On the left side, function is defined. So what are those 2 points? One is 0 and other is minus 1. So at these 2 points, we will calculate the value. A functional value, we will calculate the left hand limit, we will calculate the right hand limit. If all three are equal, then of course the function will be continuous at that point, else not. So what I am doing is, first let me calculate 0 plus. 0 plus here, yes, what my function is, please see, my function at 0 plus will be x tending to 0 plus, it is minus 1. So it is minus 1, okay. Limit x tending to 0 minus fx. On the left side of 0, my function is defined like this, minus 2. So what I will find, limit x tending to 0 minus how much? Minus 2x minus 1. Let me see what it gives you. Here put x is equal to 0, because this is the polynomial, limiting value will be equal to the functional value. So it is minus 2 into 0 minus 1, so again it is minus 0. And then what is the functional value at 0, please student? Please see, it is for greater than 0, it is equal to minus 1. All three things are equal. Left hand limit, right hand limit is minus 1, left hand limit is minus 1, function value is minus 1. So the function is obviously continuous at minus 1. Similarly, you have to show that yes, your function is continuous at minus 1. Let us see, check whether what is the continuity at minus 1. So what then you need to show is limit x tending to minus 1 plus, let us calculate, function. Function is, so limit, it is x tending to 1 plus minus 1, please see, minus 1. So function at minus 1 on the right side is like this, it is minus 2x minus 1. So put here minus 1 please. So what you will get? Now see, here also you had to be very justified. Why you are putting it? Yes, it is a polynomial, and in polynomial limiting value is equal to the functional value, and that is why you are justified in putting at place of x minus 1. So minus 2 into minus 1 and minus 1, so minus plus 2 and minus 1, it is plus 1. Okay, and then let us likewise calculate the limit at 1 minus 1, and on the left hand limit of this thing. So let us see what it is. On the left side, the function is defined to be what? In what manner? It is plus 1. It is plus 1. So it is plus 1. And what is the functional value? Functional value at minus 1. functional value at -1, how the function is defined, please see. I think it should be -1 is less than x is less than 0. Please see function here. Here it is like this only, so it is -1 again. Why -1? Because see, even if x is -1, so this thing is 0, you can replace it by this model x plus 1 is to be replaced with minus this thing x plus 1, because only when it is negative then you are going to replace it with minus x plus 1, else you will be replacing it. So all these three values are plus 1, so therefore function is continuous at 1 also. So it means this given function is continuous is continuous on all the real time. So with this thing, see, we have finished this exercise 5.1. Now quick, we will move on to differentiability, which is another important topic for you people to understand it in its entirety. Now, so few things we have really read as far as your class 11 is concerned, but I quickly summarize it as my way of teaching is like this only, because I don't want you to be found wanting anywhere. Let me just have a glass of water and then I can. So differentiability. Yes. So up till now what you have learned is its definition. Fine. Its geometrical interpretation you have also learned it. And then see through the fundamental definition you have tried to obtain the differentiation of certain functions like trigonometric function, x to the power n and so on and so forth. Elementary function, their derivatives you have derived. And then I think you have also done productive and quotient rules in class 11th. So basically I have checked in, and what I found was that from your class you had to start with the differentiability of the composite functions, and then implicit function, and then inverse trigonometric function, and then logarithmic differentiation, and so on and so forth. But then see, let me take up the vital points which you have already learned in class 11, because that is essential to have a full grasp of the things. So here I take up first of all the definition. A function, suppose some fx is some function, and you say that it is differentiable at a point, say x naught, when if fx naught plus h minus fx naught upon h, this is your this thing, and limit x h tends to 0 if this exists. If limit this exists, this limit exists, we say function fx is differentiable at x naught if this limit exists. This limit exists. Okay. Now this is what this function is. It is basically, if you look at what this thing is giving you, if you look at the numerator part, if forget about this limit, only if you concentrate on fx naught plus h minus fx naught, then let us see what it is giving us. It means you are making a change in the value of the function. I am not taking h tending to 0. As I have said, I am ignoring this limit as tending. So it is, numerator is simply giving you the change in the value of function. And this change in the value of function has been done from where to where? From point x naught, you have taken it to x naught plus h. Now h could be assigned any value. So this numerator is giving you change in the value of function. And this h can well be written to be like this also, x naught plus h minus x naught. See, instead of writing the numerator simply h, better write x naught plus h minus x naught. So what is the denominator giving you? Let us see. It is simply giving you the change in the value of function. It is simply giving you the change in the value of variable. Sorry, not in the function. Numerator is giving you change in the value of the function when variable has been changed from x0 to x0 plus h. So basically, denominator is giving you change in the value of variable. Numerator is giving you change in the value of function when your variable has been changed from say certain numerical value to certain other numerical value. Okay, and then see you are dividing it. So what it is giving you? It is giving you rate of change in the value of function with respect to change in variable. Please see, the word rate is important. Rate means what? Rate is always with respect to something. And like 6 bananas cost say 12 rupees. So what is the rate of bananas? This 12 bananas you are dividing by rupees. So by number of bananas. So what you are getting 2 rupees per banana. 2 rupees per banana. That is the rate which you normally call it. So here see, you forget about limit. Forget about limit. I am simply talking about this thing. So what you are doing here, it is simply the rate of change of function with respect to change in the value of variable. Change in the value of variable. I am not saying that you are changing your variable to 0. So see, but then see. So if this limiting part you forget, I am removing it right now. If this much of thing would have been given to you, then what you would have said? You would have simply said that it is the rate of change of value of function with respect to change in the value of variable, because your function is depending upon here h right now. Okay, so this is one way of saying it. Now let us see what this thing is. Limit s tends to 0. When you write it, so it means that what we are more interested in, that we are interested in rate of change of value of function with respect to variable when this change is infinitely small. Please see, when this rate is infinitely small. And I will tell you that what is the advantage, that when this rate is infinitely small means tending towards 0. They were tending towards 0, then let us see what this rate of change of value of the function with respect to variable gives us. See, in very important result, I will give you a very practical example of the thing. Here see, suppose you know what is this what is this speed and what is this instantaneous velocity. See, if you look in what is this velocity and this is this instantaneous velocity, then see velocity or let me take a speed. I am not attaching the direction therein. Okay, because the difference between speed and velocity, suppose a particle is moving in a straight line. So direction, if I am also assigning, then the speed is nothing but your speed plus direction is your velocity. So speed is nothing but see, suppose I give you the distance function. Distance function t means suppose t at 0, it is like say t square plus 3t, like this thing. So what this distance function is giving me? It will tell me, and see the linear motion. It is the linear motion. A particle is moving like this, and this is the function through which I am describing the distance of the point, and the distance is measured from a reference point origin. So basically what it is, suppose if somebody asks me where the point would be at 1 second, so at place of t, I will put 1 second. So 1 plus 3 into 1, so 4, it will be 4 centimeters away from origin. So at any point of time I can find where my particle happens to be through this my function, this distance function. Now see, here see, suppose t naught is some point, t naught plus delta t minus d naught upon this thing t naught plus delta t and minus t naught if I write it. Then what it is giving me? Please look in. It is giving me the numerator is giving me the distance traveled in how much time? T naught plus delta t minus t naught. I have started counting my time from there, t naught. And then how much time I am taking into cognizance? Delta t times. So this is the distance traveled in t naught plus delta t times. This is the distance traveled in t naught time. So if I am subtracting it, so this numerator is giving me what? Distance traveled in time delta t. And what is this thing? This is delta t. T naught cancels effectively in denominator. You are getting delta t. So speed is what? Distance travel upon time taken. So this is giving me the speed. This is giving me the speed. Of course, see, if I since it is moving in the linear direction, if I attach the velocity also there, then this is giving me the velocity. Okay, but then see that you have a wonderful concept, because see what actually happens is practically that when we are going somewhere, then all the way we are not going with a uniform speed. At times we are fast, at times we are slow, at times we will be stationary also, because suppose we have to buy a certain thing, then we have to stop at there. So our velocity or say speed is zero right at that particular moment. So here see the relationship between instantaneous velocity and velocity is what? Well, at instantaneous velocity, you are more interested in getting the velocity at a particular time period. So instantaneous velocity, for calculating the instantaneous velocity, what you need to do is, again see, you had to calculate the average. You have to take some time span, and that time span will be infinitely small. The smaller the time span, the better instantaneous speed at that particular moment you would be getting. Suppose I wish to know that after 3 minutes, what was my speed? So what I will do, here is my function, dt function, at 3 minutes I will take 3 plus 0.001. Suppose I take 3.1, means just one fraction, 3 plus 1 second, 4 second, suppose I take it, and then I take subtract it from 3 second, my distance travel in 3 minutes. So, and then delta t, let it be 1 second. So, okay, and then see if I further reduce it to 0.01, then I will get a better approximation to my instantaneous speed, because earlier I was calculating that this thing. When I was taking 1 second, I was calculating this average speed over the 1 second, beginning from 3 minutes. But if I reduce it to 0.01 second, then I will be taking an average speed from calculated when I was from 3 minutes. So the more the smaller interval I take, the better approximation towards instantaneous speed I will be getting. And so that is why, see, this is a classic example where, of course, you can well understand that what is the advantage of taking this limiting value. For limiting value, you exactly get the instantaneous, right at that particular moment, what had been the rate of change of the value of the function with respect to variable. That aspect, if you had to find it out, while studying the motion of the particles, molecular particles, of course, these things matters a lot. So this is what the physical example of this thing is. So in a way, this is what differentiation means this thing. So this is one thing which I intend telling you was. And so if somebody asks you what is this interpretation, and then see the most important interpretation is the geometrical interpretation of this differentiation. Here see, suppose this is the graph of some function, and you want to find its derivative here. Suppose this is some graph y is equal to fx. Y is equal to fx is some graph, and this is x. Suppose x naught. Here the functional value is what? Fx naught. It is fx naught. Okay. Then what you will do? You are calculating. See this thing x. This is say x naught plus h, and okay, so this much. So this much of thing here, and this is how much h. This is h. So please see, it is giving you tangent theta means this much of thing. This is what, if I take it, then this will be what? Fx naught plus h minus fx naught. This is h, please see. So this much is, so this is tangent theta of this thing, this line. If I join it, then this thing. And you know, when h tends to 0, because if you see what is this tangent at this point, if I need to find it out, then what, this is my point P, this is my point Q. Then this point Q has to be moved on this, while of course destined into the curve, towards P, and that is how we obtain the tangent. So the geometrical interpretation of this differentiation is that it gives you the slope of tangent. It gives you what? Slope of tangent, because here the suppose at this point P, suppose this theta is the slope, and tangent theta is nothing but the value of the derivative at the point x is equal to x naught. So this is the geometrical interpretation. So here please remember how a tangent is drawn to a curve. That is a very important thing, and that you need to understand. And once you understand that how tangent is drawn, I am just showing it to any graph here, then you will understand, you will have no problem. Suppose at this point I have to draw the tangent at the point P naught. Then what I will do? I will take a point Q. I will take a point Q, and then I will join this PQ, okay, by a straight line, okay, and then this line PQ will be like this thing, okay, this thing. Then the slope of this line is say theta. Then I will bring Q further closer to it. Then my PQ line will be like this. And so please see, this my line will be like this. Earlier it was like this. Okay, I will further bring it closer to Q. Then see my line will further change. My line will further change. Okay, so under limiting condition, when Q has been brought infinitely close to it, then whatever the line I will get by joining this point PQ, then the slope of that line, the slope of line is like this is theta, and tangent theta also is precisely gives me the value of the derivative. So this is, I will explain you this particular aspect on some other day as well, but in a brief, this is what is the geometrical interpretation of the derivative. And with these two things in mind, this has been covered as far as in your class. Now see one important thing, this thing, the proofs, regarding the proofs, that how this, that the sum of two function is given, then the derivative of the sum of two function is equal to the sum of their individual derivatives. And if the product has been given, that product rule, first function into derivative of second plus second function into derivative of the first, quotient rule, all these things. So quickly we will go through this so that we are comfortable herein. And what you will see that in this exercise, there is hardly anything provided you have acquired the perfection on the theorems of these limits, which we have so assiduously tried explaining you. So now see, suppose there are two functions, f1x and f2x, and this thing. And this is the sum of the two functions. You have to find its derivative. It's derivative of the sum of two functions. Then why it is equal to the sum of their individual derivatives? It's too simple to prove. Because if d by dx of f1x plus f2x, so what it becomes? It will simply become what? By definition, f1x plus h plus f2x plus h, okay, minus f1x plus f2x in other bracket, okay, and whole upon h, and then this whole thing closing and then limit h tends to 0. And this thing can be rewritten as f1x plus h minus f1x. From here we have taken f1x, and this thing we are putting in one bracket, and the rest of the things we are putting in the other bracket, f2x plus h minus f2x, and then upon h, and then this whole thing, and of course see limit h tends to 0. Now this much of thing we are taking to be one entity, this thing to be we taking to be other entity, and the limit of the sum of two functions is equal to their individual limit, and that is why what it will be, limit s tending to 0, f1x plus h minus f1x upon h plus limit h tends to 0, this whole thing, f2x plus h minus f2x upon h. Okay, so this is how, and this is what? This is d by dx of f1x, and this is what? D by dx of f2x. So this is how you have shown that the derivative of the sum of two functions is equal to their sum of their individual derivatives. Likewise, see this product rule which you have done. We can prove it. So simple they are. But then see, you need to understand, and that is why I have been time and then telling you that this theorem on the limit, of course, if you can master it, then see here, this thing, this entire property will come into handy. So now see, I have to find the product rule. Let us see how you have been doing it. But before I actually take this derivative product rule or quotient rule, I would like to prove one theorem. Okay, till that time I will immediately prove after this that yes, if a function is differentiable, then it is continuous. It is continuous. Okay, but the converse is not true. If the function is continuous, then it may not be differentiable. And this is a very important result, and I will prove it. In fact, I should have taken this the proof of this thing first, and then okay, let me take it. The proof will hardly take much time. So what it is? Yes, it says if a function is differentiable, then it will be continuous. Okay. Please see, and the converse is not true. So write down, this is a very important theorem, and the proof you should know it. If f is differentiable, yes, then this implies f is continuous. F is continuous. So let f be differentiable at x is equal to x naught. This implies limit fx naught plus h minus fx naught upon h exists, h tending to 0. This limit exists. Say it is equal to L. Say it is equal to L. Because see, it has been given that function is differentiable at x naught, so naturally this limit will exist. Now once this limit exists, then please see again for understanding it. See, in your book they have given some proof which of course does not employ the rigorousness of the mathematics, but here see I will tell you. Now this function, this limit exists. Suppose this whole you don't, this is one function, this function limit is L, then what will happen? For every epsilon interval of L, we will be able to get a deleted delta neighborhood of H, such that whenever x falls within that deleted delta neighborhood, then functional value will fall within that epsilon neighborhood. So this is what we are going to do it. So now see, so what I will choose, some epsilon neighborhood of I am choosing, then correspond, because this limit exists, so for every epsilon neighborhood of L, I would be getting a deleted delta neighborhood of this H, 0, around this 0, so that whenever H belongs to that deleted delta neighborhood of 0, then functional value will fall therein. So it means that, please see, functional value is falling. So my function is what? This much of thing. Please see, fx naught upon h. This thing will lie between where? Between h plus epsilon minus L minus epsilon. Epsilon neighborhood. See, please recollect the geometrical definition of this epsilon neighborhood. Means that this functional value, this is your function. This will lie between L plus epsilon, L minus epsilon to L plus epsilon. Whenever, what will happen? Whenever 0 is less than, yes, h is less than, mod h is less than delta. So it is that 0, this h lies between minus delta and delta, and of course it should be deleted, and h is not equal to 0. H will not be equal to 0, that is there. That is why it is called deleted delta neighborhood. So this is the thing. Whenever h lies between minus delta and plus delta, see then your functional value will lie between L less epsilon to L plus epsilon. So this is what. Now with this understanding, what we need to do it. Let us multiply it. So what we will get, h L minus epsilon is less than f x naught plus h minus fx naught. This thing let us write within the bracket, and this thing will be what? H L plus epsilon. L plus epsilon, whenever of course see this thing is happening. Whenever this thing is happening, I am writing here. Okay, now see what I will do. Yes, now h is tending, now let h tends towards 0, then calculate the limit. Calculate the limit of these inequality. Limit h tending to 0, h L minus epsilon will be less than limit h tending to 0, this whole thing, that is fx naught plus h minus fx naught okay, and less than what h this thing limit h tending to 0 h into I plus epsilon. Now please see students, this L minus epsilon is what? Constant. It can be taken outside and limit as tending to 0 h. H is a polynomial. So this will be 0. L minus, see, this will be 0. It is just like constant into your function. Here what is h is tending towards 0. So it is a polynomial in h. So this limit will be 0. This limit you write as such. Limit as tending to 0 fx naught plus h minus fx naught. This limit don't calculate, keep it as such. And likewise here, this h, this is a polynomial in h. This L plus epsilon is some constant. So this constant can be taken out, but so this limit will also be 0. And therefore by sandwich theorem, this limit is lying between 0 and 0. So obviously this limit will be 0. So obviously this limit will be 0, making use of the sandwich theorem, because sandwich theorem precisely says that if a function is embedded between two functions and if you are calculating the limit of the function at some particular point, and the limit of the two functions between which your given function is embedded, and if the limit of both these two functions between which the function is embedded are equal, then the function of your given function will also have the same limit as that of the function between which they are embedded. So this is what how we prove that limit as tending to this thing is 0. Now here again I would like to explain you. You have to prove your function is continuous. Your function is continuous. Let us see. Does it convey the same thing? Does limit h tending to 0, limit h tending to 0, what you have shown? Yes, x naught plus h minus fx naught. What you have found that this is 0. Okay, very good. So now we have to prove what? That function is differentiable at x naught, and you have to show that the function is continuous at that point. Yes. Now we have to proceed further. Now this limit is, this is one function, this is limit of addition of two functions or subtraction of function is what? They are individual limits. So this thing can be written to be what? This is fx naught plus h minus limit x tending to 0 fx naught is equal to 0. So what you have shown, limit h tending to 0 fx naught plus h, x naught plus h is equal to limit x tending to 0 fx naught. So please see what it is. Now this is continuity. This is what you are showing continuity. What is the functional value? Okay, whatever this thing, limit of this thing. Now this is what? Here if you take assign h, you are assigning some positive value, then this is the right hand limit around 0. This is the right hand limit. If h you are assigning left hand limit. So if this is conveying you that both left hand limit and right hand limits are equal to this thing. And what it is as tending to 0? Fx naught will be a perfect value. So this is fx naught only. Please see, limit as tending to 0 fx naught is what? It is fx naught. It does not contain anywhere h. So this is fx naught. So what you are conveying is that both left hand limit and right hand limit are equal to the functional value, and as such, this is what the demand of the continuity is. That both left hand limit, right hand limit should be equal to the functional value at x naught. And therefore, now the proof is complete. Now the proof is complete. So this is what we had, a very vital result which we had to take into consideration. With this thing, I will quickly give you the proofs of this thing, and then I will proceed on my next lecture. And then my next lecture probably will be tomorrow itself, because I missed it yesterday because of account of the power failure. So now quickly I will take two results and then I will stop it. D by dx of that product rule which you have followed, f1x into f2x, its derivative you have to determine it, and you know that how it comes. You say that first function into derivative second plus second function into derivative first. Easy to see what it is, d by dx of this thing. This thing is nothing but f1, okay, let me write here, f1x plus delta x minus f2 x plus delta x minus f1x and f2x upon delta x, and this thing closed and this thing, and then write limit as tending to 0. Okay, this thing you can further write, see limit s tending to 0 what? f1x plus delta x, f2x plus delta x minus f1x and f2x plus delta x. This thing you add and this thing you subtract, minus f plus f1x, f2x plus delta x, and then copy same thing, minus f1x, f2x. So and then close it. Okay. So this is what? Limit and whole upon h. Whole upon h. Okay. So this is what? Limit s tends to 0. And here see, from these two terms, see there are two terms. What I have done, I have added f1x, f2x plus f subtracted, and these two terms will cancel. And there I have copied it as such. So now see, what is that? What is why I am doing it? Now from these two terms, what I can take common is f2x plus delta x. I can take common, and here is within the bracket what I will get is f1x plus delta x minus, you see, here I will get this thing, and here what I will get minus f1x upon mh. I will write here. Okay, this is one thing, and first let me write it. Plus, and then here see, from these two terms what I will take common, f1x. f1x I will take common, and what I will get here is f2x plus delta x minus f2x upon h. This thing I will get it, and this whole thing of this thing. Okay, now see, this is one part, this is one entity, this is another entity. So limit of the sum of two functions will be equal to their individual limit. So what I can write on the next step is that this is nothing. I will write on the top here so that I may get the entire proof for you people. So here see what it becomes, limit okay, h tends to 0, yes, and f2 x plus delta x into f1 x plus delta x minus f1x upon delta x. Oh, I am writing delta x. Please see, not it is delta x, because I am taking not here. I have written delta x, so I will put delta x tends to 0. Okay, so delta x upon delta x, and then plus limit of f1x and within bracket f2x plus f2x plus delta x minus f2x upon delta x, and this whole thing. Now we are not to put them within the brackets. We can remove the brackets because these are two entities. Now here also, please see, each of these entities, this whole limit is the product of two functions. One is this one, other is this one. Likewise here, this is one function, limit of delta x tends to 0, and this thing. Here also I have to change delta x. So limit of product of two functions, again I can write to be what? Limit delta x tends to 0, f2x plus delta x plus delta x into limit delta x tends to 0, f1 x plus delta x minus f1x upon delta x plus limit delta x tends to 0, f1x, and limit delta x tends to 0, f2x plus delta x minus f2x upon delta x. Yes, this much of thing you have to write it. Now please see, you have almost got the result. See, yes, what it is, please see, f2. Here see, when you have taken, it was given to you that individual derivatives of both the function exist. Means derivative of f1 exists, derivative of f2 exists. So limit of delta x, f2x plus delta x, what it would be? So since f2 derivative of f2 exists, as said by our previous theorem, f2x will be a continuous function, and therefore f2x plus delta x under limiting when delta x tends to 0 will be what? f2x. Okay, see, it is a continuous function at x, so f2x, and see, in fact I should have taken x naught, then things would have been more better clear to you, but hardly means whether you take x or x naught hardly matters. X denotes any point. In fact, I should have taken x naught because at the first time it would have been easier for you, but no issues. And here what it is? Here, because it is continuous. See, this aspect unit, it is continuous, and therefore you can, here, f2x plus delta s will be f2x only. And this is what? Derivative of d by dx of f1x. And likewise here, what it is? This is f1x, delta s tends to 0, f1x you write first function, and this is what? Derivative of second function, f2x. This is how you will be getting it. I won't be taking much time because then I find too difficult for uploading my videos. The question rule you would please similarly try, and then from the next term we will tomorrow we will take up the composite function question therein, and then we will take the implicit function. This proof of the composite derivative of the composite function, of course, see, each one of you should know it because it is very important. Tomorrow I will give the proof of this thing. Please make sure that the theorems which I have told you regarding the function of function, that should be clear to you. Then of course see, it will come very handy to you. Thank you.